Stars form from an enormous cloud of gas, mostly hydrogen and helium, pulled together by gravity. As the gas collapses under its own weight, the core becomes so hot and dense that the atoms ionize into plasma. In this extreme environment, nuclear fusion begins, turning hydrogen into helium and releasing an immense amount of energy. This energy pushes outward, balancing gravity and making the star shine for millions or even billions of years. Essentially, a star is a delicate balance. Gravity wants to collapse it, and fusion pushes outward. Over time, the star runs out of hydrogen in its core. It then begins fusing heavier and heavier elements: helium, carbon, oxygen, and so on. Each stage releasing energy that keeps the star shining. But eventually, the star reaches iron, the point where fusion can no longer release energy. And this is the central question of today's video: why fusing iron doesn't release energy? Part 1. Fusion and energy production basics. Why does fusion release energy? The answer lies in binding energy. Binding energy is the energy required to completely separate a nucleus into its individual protons and neutrons. The higher the binding energy per nucleon, the more tightly packed and stable the nucleus is. For example, hydrogen has a binding energy of 0 MeV per nucleon because it only contains one proton, there is nothing to bind. Deuterium has a binding energy of 1.1 MeV per nucleon because there is now a nuclear bond holding the two particles together. Helium-4 has a binding energy of 7.1 MeV per nucleon, much more tightly bound. When lighter nuclei fuse into a heavier one, the resulting nucleus is more stable and has a higher total binding energy, meaning a fraction of the mass has been converted into energy. But why the atom lose mass after fusing? To make the nucleus more stable, the system must lose some of its energy. Because mass and energy are equivalent, this energy comes from a tiny reduction in mass. The lost mass is released as energy. Example in the Sun. 4 hydrogen nuclei eventually fuse together to form one helium-4 nucleus. Let's look at the calculation. The mass of 4 protons is 4.0313 U, with U meaning atomic mass units. The mass of helium-4 nucleus is 4.002603 U. The mass of helium-4 nucleus is slightly smaller than the total mass of the 4 protons that created it, with a mass difference of 0.0287 units. Now, using Einstein's famous equation E equals mc squared, and knowing that one atomic mass unit, or U, equals about 931.5 MeV per c squared, we can convert that mass difference into energy. E equals 0.0287 times 931.5 equals 26.7 MeV. So about 26.7 MeV of energy are released every time 4 protons fuse into one helium nucleus. This is the energy that makes the sun shine and power stars every second. Part 2. The binding energy curve. To understand why fusion stops at iron, we need to look at something called the binding energy curve. In a graph where the vertical axis represents the binding energy per nucleon and the horizontal axis shows the atomic mass, basically how heavy the nucleus is. At the very beginning of the curve, with hydrogen, the binding energy is extremely low. As we move towards helium, it rises sharply, meaning that fusing hydrogen into helium releases a lot of energy. Then, as we go through elements like carbon, oxygen, and silicon, the curve keeps increasing, but more slowly, until it reaches its peak at iron 56, with a binding energy of about 8.79 MeV per nucleon. This peak is crucial. It tells us that iron 56 is the most tightly bound and most stable nucleus in nature. That's why fusing element lighter than iron releases energy. They're climbing up the curve toward a more stable state. But once we reach iron, we're at the top. Fusing iron or heavier element doesn't release energy anymore. What happens if we try to fuse them into a heavier nucleus? The thing is that there is no nucleus with 112 nucleons with a higher binding energy per nucleon. Any combination will be less tightly bound than iron 56. That means, instead of releasing energy, the reaction will require energy input. Iron 56 is essentially the end of the line for fusion. So in conclusion, Lighter elements like hydrogen release energy when fusing because the resulting nucleus is more tightly bound, so more stable, and because it's more tightly bound, it has to lose a fraction of its initial mass to reach this lower energy state. That lost mass is converted into energy that pushes outward. But with iron, the nucleus is already at the peak of binding energy. It's as tightly bound as nature allows. So instead of losing mass and releasing energy, fusing iron will actually require an input of energy. That's why fusion stops there, and this is why stars cannot generate energy by fusing iron. Once a star fills its core with iron, fusion stops, pressure drops, and gravity takes control, and it's the beginning of a supernova. Thanks for watching. You can support me by liking and subscribing, and see you next time.